Sounds even better. Okay.
Yes.
Click that.
We're waiting to see what happens, I think.
I'm sorry, I heard someone speaking.
Jumping us.
So Professor Fredriksson, if you want to begin to share your screen.
Yeah, I can share my screen.
Go ahead.
So can you see my slides?
Yes, we can.
Very good. Okay, so then I'll start, if that's okay.
Okay, well, let me introduce just a moment and explain to the group. Okay, good afternoon or morning, wherever you might be. My name is Robert Borgstrom, and I have the pleasure of moderating this session on climate policy. We've got 4 speakers who will be speaking in the order presented in the program. Everyone has 20 minutes to speak, and after that, we will have a Q&A period of about 5 minutes. So we will try to get through as many as possible. We ask that you put your questions on the screen so that we can see them and try to proceed through that. Okay, with that in mind, I'm happy to introduce the first speaker. The first presentation is Distributional and Efficiency Impacts of Higher EU Climate Targets. And the presenter is Gustav Fredriksson of ETH in Zurich. Mr. Fredriksson, you have the floor.
Thank you very much. And let me start by saying that it's fantastic being here, and this is a great opportunity to present this paper. So this is a joint paper with Florian Landis and Sebastian Rausch, and it's work in progress. So we're very happy to receive any comments and feedback that you might have to improve the paper. So
Yes, sorry, Professor, can you put the slides in the big plan, because you are seeing the next slide also background and the first slide just before beginning.
Sorry, I can't hear you.
We are seeing the screen, the first slide that you're presenting, also the next slide, we are seeing the trial version. So can you put the normal presentation? Can you, or yes? Okay, no. Yes. Yeah, it's that.
We see the presentation mode of your slides. Maybe you have 2 screens and you have to change.
Yeah, I have only one.
Why don't you try the icon at the bottom of that screen and see if that does it.
Still an issue?
Yeah, Gustav, if you close it again, and there's a checkbox at the top right that says use presenter view. If you uncheck that one.
So
right on the left of your mouse, right. There it is. And then you should see the full screen version. There you go.
Okay,
success.
Is it better?
Yes.
Much better.
Thanks.
Okay.
Thank you for.
Please continue.
Okay, well, I feel like it wouldn't be a virtual conference without some hiccups on the way. So yes, we're on track.
A very minor hiccup. So
indeed. Thanks for the help. Okay, so I'm happy you can see my slides now. That's very good. So the background to this paper is really the 2030 climate target plan, which the EU published at the end of last year. And in this plan, the EU proposed to increase its 2030 emissions reduction target from 40% to at least 55% above 1990 levels. And carbon pricing was identified as an important part of the new strategy to achieve the higher target. So a key question surrounds how existing carbon pricing schemes in the EU should be amended to absorb the additional abatement from the higher 2030 target. So there's in particular a need to consider how the additional abatement should be spread across sectors. So by this, I mean between ETS and non-ETS sectors and across member states through the effort sharing regulation targets of EU countries. There is furthermore a need to understand the impact of greater carbon market integration in Europe, as this was highlighted as a potential policy reform in the climate target plan. So 2 criteria for assessing the options of where to assign the additional abatement. The first, so I'll discuss 2 here. The first one, which we think is relevant, is the overall cost of the policy design option. And it's well recognized in the literature that the overall cost of the efficiency depends on the extent to which marginal abatement costs are equalized across polluting sectors and countries. So in segmented markets, so the segmented non-ETS market structure we have today, for instance, this implies that we should assign the additional abatement to where it is cheapest. And we can further improve on efficiency, at least in theory, through market integration, since this is one way of fully equalizing marginal abatement costs. But obviously, efficiency is not the only yardstick that should be considered. We also have to look at the distribution of cost, both across and within countries. And already today, EU climate policy is designed to compensate lower income member states. So for instance, through the ETS auctioning shares. And any adverse distribution effects within countries should be addressed such that it's not the poorest households in EU member states that are most hurt by carbon pricing schemes, because this can jeopardize the political feasibility of carbon pricing. So this brings me to the research question of the paper, which is, what are the efficiency and distributional effects, both within and between EU countries, of different EU carbon pricing policy design options in the context of a 55% abatement target? And by policy design, we mean 3 things. The first one is how should the abatement be split between ETS and non-ETS sectors? The second one, what should the non-ETS burden sharing rule look like across countries? So how should the abatement be spread across countries? And the third aspect is what are the implications of a higher degree of carbon market integration compared to today? Our paper makes 2 contributions. We think the first one is that we're one of the first analyses that looks at the distributional implications of aligning European carbon pricing policies with a higher 2030 target. And in doing so, we shed new light on how different burden sharing rules across both sectors and countries affect household and country incidents. Our second contribution is that we contribute to the literature on integrated carbon markets. This literature has largely ignored household incidents and has instead typically focused on aggregate outcomes, such as the impact of market integration on efficiency. So let me quickly describe the model that we're using. It's a fairly typical GTAPing GAMS model type. So it's a static multi-sector, multi-region numerical general equilibrium model, which is solved as a mixed complementarity problem in GAMS. It consists of 10 sectors, including 4 primary energy sectors and 31 regions. So we have all the EU member states in there. We have the UK, Norway, Switzerland, and a composite region, which we call the rest of the world. The production and demand functions in our framework are characterized by constant elasticity of substitution. And we model trade using the Armington approach, whereby domestic and imported varieties are imperfect substitutes of each other. Households in the model, they have a fixed endowment of labor, capital, and natural resources. And we assume that these production factors are perfectly mobile within regions, but immobile between regions. And we incorporate income deciles in our model for 21 regions. So these are the regions for which we have household level data. And for the remaining regions to model household demand, we use a representative agent. So revenues recycled within countries in proportion to benchmark expenditure shares. And across countries, the revenues recycled according to faithful rules for ETS revenue. And we calculate these rules ourselves using the rules that are stipulated by the European Commission, and according to non-ETS allowance shares for non-ETS revenue, if non-ETS markets are integrated in our analysis. It's important to note that our model only takes into account the direct costs associated with decarbonization. So we're not capturing the benefits from averted climate change harm or any of the co-benefits from emissions abatement in our model. In terms of data, we're using economy-wide macroeconomic and energy data from GTAP version 9, and we're complementing this with household level data for 21 European countries from 2 Eurostat surveys. The first one is the household budget survey, the HBS, which contains household level data on consumption expenditure. And the second survey is the EU Silk, which contains household level income data. And what we do is that we manually group households, we sort them into income deciles, and that gives us detailed consumption and income data for 10 deciles for 21 countries. And this will be the basis for our within-country analysis. In showing the results, we will always show them relative to a baseline. And this baseline reflects a situation whereby the EU does not go for a higher 2030 target. So the baseline assumes that the EU abates 40% of its emissions, and it assumes that the prevailing ETS and non-ETS abatement split exists, so that the ETS accounts for the current share of abatement and overall abatement in Europe. We assume that the member states in its non-ETS sectors abates according to their non-ETS targets that are stipulated by the effort sharing regulation. And we assume the segmented non-ETS market structure that we currently see in Europe. Then we develop various scenarios that we compare the baseline to. And in all scenarios, we assume that the EU goes for a higher target, so a 55% overall abatement target. And the scenarios differ in three dimensions. So we look at different ETS targets, and the ETS targets really reflect how you spread abatement across sectors. So a higher ETS target reflects that you shift abatement towards ETS sectors, and the lower ETS target means that you shift abatement towards non-ETS sectors. Then we also look at the impact of different non-ETS targets. So this is the regional burden sharing rule. And finally, we look at 2 different degrees of non-ETS market integration. So the first one, which we call no trade, is this baseline assumption that non-ETS markets are segmented. And then we develop an additional scenario, which is trade, whereby all countries integrate their non-ETS markets. So in presenting the results, we often also group countries to improve legibility of our results into 3 categories, and they're shown here. So it's low-income countries, middle-income countries, and high-income countries, we call them. And they're essentially sorted based on their 2011 per capita income at purchasing parity. So just so you're aware that these are the countries in each group, and these are just arbitrary names that we give them. So let me show you the between country results. If we start with the decision of which sectors to assign the abatement to. So you should be able to see my mouse here, that's good. On the y-axis here, we see the percentage welfare change. And on the x-axis, we have different ETS targets. And the 58 target reflects the current ETS abatement share that we see today. But these ETS targets are expressed in terms of 2011 emissions. So yeah, they're not that useful, I think, to think about in terms of an ETS target, but they rather just reflect the share of abatement that's carried out in ETS sectors versus non-ETS. So an ETS target above 58 reflects that more abatement gets shifted to ETS sectors, and a lower target means that abatement shifts to non-ETS sectors. And then we have the 3 different country groups here. And an interesting finding in this picture is that low-income countries prefer an ETS target of 58%, whereas middle and high-income countries favor a lower ETS target. So middle and high-income countries favor shifting more abatement to the non-ETS than poorer countries. And we wanted to explore why. So what we did was we broke down this total welfare change into 2 effects, which is this additional y-axis here. So these bars essentially sum up to the total welfare change. On the one hand, we have something which we call the abatement effect, and on the other, we have the revenue effect. And the abatement effect essentially reflects the change in abatement costs. And we see that it's always negative because we have a higher overall emissions reduction target in Europe. So we're going to have higher abatement costs independently of where we assign this abatement. The revenue effect denotes the change in net allowance export revenue. And we see that it's positive for low-income countries. And this reflects their position as net exporters of ETS allowances. And this revenue effect gets stronger for low-income countries as the ETS target grows. And the reason for this is that a high ETS target pushes up the ETS allowance price, which gives the low-income exporting countries more revenue from selling allowances. And it's essentially this revenue effect that explains why low-income countries prefer more ETS abatement compared to the rest of the EU. Moving on, we can also look at the impact of different regional burden sharing rules. So again, we have the different ETS targets down here. The black line is the same as before. And you can think of the black line as if the current non-ETS targets are just scaled up by the same factor to meet the higher 2030 target. The green line, on the other hand, shows what would happen if we allocated 20% more allowances to low-income countries, whereas the blue line shows what happens if we take away 20% of their allowances and give them to richer countries. And here I'm talking about non-ETS allowances. And an interesting finding here is that if we reduce the non-ETS burden of low-income countries, then we see that they increasingly favor shifting more abatement to the non-ETS, just like their richer counterparts. So you see that for the green line, they're more or less indifferent between a 50 and a 58% target. And the reason for this is that when you reduce their burden in the non-ETS, then it becomes cheaper to abate there. So then they favor shifting more abatement to sectors where it's become cheaper. We also
5 minutes.
Okay, thank you. We also look at the impact of increased market integration. And there are 3 findings from this figure, I would say, or three insights. The first one is that moving from no trade to an integrated non-ETS market again makes the sectoral abatement preferences more similar across countries. And the reason for this is that low-income countries become net exporters of non-ETS allowances as well. So they gain a non-ETS revenue effect when markets are integrated, which means that they benefit from a higher non-ETS price. We also see that, so the second observation is that it's especially low-income countries that gain from market integration. And third, efficiency also increases as average welfare increases. So we do not find any trade-off here between equity and efficiency when it comes to integrating non-ETS carbon markets in Europe. Now, let me quickly go through the within-country results. So here are the 21 countries that were available for analysis. For each country, we have 10 deciles, and they're not shown for legibility reasons. And on the y-axis here, we have the percentage utility change. And what I want you to take away from this picture is that independently of how we allocate the abatement across sectors, we have a progressive incidence within countries. So the downward sloping line suggests that regardless of the ETS target, it's always the poor households that are relatively better off compared to the richer households. I would say the one exception is Romania in our model. Similarly, the regional burden sharing rule doesn't affect incidence too much. We typically have progressive incidence. And the same goes for the degree of market integration. And another interesting insight here is that it's especially the poorer deciles in low-income countries that benefit from the non-ETS market integration. You can see this comparing the difference between the blue and the black lines for the leftmost 10 countries here. And the reason for this that we find, which we're not showing here, but we explain this as we attribute this to the fact that low-income countries are more shielded from factor income losses when the market integration pushes up the non-ETS carbon price in these countries. And they're more shielded from factor income losses because they derive a higher income share from transfers. So let me conclude, because I think I'm getting close to time here. We find in our paper that in segmented markets, lower income countries prefer a higher share of ETS abatement compared to richer countries, but the abatement, so the sectoral abatement preferences get more similar across countries, either if lower income countries non-ETS burden is reduced, or if non-ETS carbon markets are integrated. And it's especially the lower income countries that benefit from the market integration. So we do not find evidence of an efficiency equity trade-off from integrating non-ETS markets. Within countries, we typically find progressive outcomes independent of the way in which abatement is allocated across sectors or regions. And these progressive outcomes occur in spite of a non-progressive recycling mechanism within countries. Lastly, we find that the incidence in lower income countries further improves if non-ETS markets are linked, as it's especially the poorer deciles in low income countries that benefit from the non-ETS market integration. So with that, I thank you very much for your attention. And as I said, I would be very, very happy to receive your comments and questions.
Thank you very much. And thank you for staying within time so clearly. Be happy to entertain questions, but I have one to begin with, kind of as a personal note, because I spent quite a bit of time in Romania. Why do you think Romania is the outlier?
Yes, that's a good question. I have to admit, I have not looked into this in the past few weeks, but if my memory serves me correctly, I think it has to do with the income profile of the deciles there. So I think it reflects how the capital and labor income is allocated across the deciles. It's a bit of an irregular pattern in the microdata.
Thank you. We've got some other questions from Mr. McKitrick. Did you compute the size of leakage effects associated with, I need to click this to keep the thing on. Did you compute the size of leakage effects associated with the new target?
No, we did not. No, we did not look at leakage outside of the EU. What we do assume in our model is that the composite rest of the world abates 30% of its 2011 emissions. But no, we have not looked at leakage, but that's a very good point.
Are there other questions?
Can we speak?
I'm sorry, did someone speak?
Yeah. Can we ask the question using the microphone?
Yes, you can.
Okay. Thank you very much. I'm Govinda Timilsina from Washington, D.C. I have three quick technical questions. The first one is that you assume there is you restrict the mobility of the factor of production between the country. How realistic it would be within the EU countries? I mean, there is a factor of mobility within the EU, if not EU and other countries. The second is you are talking about static model, and you are going to reduce the emission by 83%. How realistic it would be? And the third one is that even in the rest of the EU, the welfare is higher at the 58% reduction than in the 33% of the emission reduction. Could you please clarify? Thank you.
So sorry, the last point I didn't get. So
yeah, so in this graph, even if you see the rest of EU,
yeah.
the welfare is higher for the 50% of the reduction compared to 33% of the reduction. If
Yeah,
I can
so
see the graph.
right. So I should have been more clear here. So these reflect the EU ETS targets, and they basically reflect the way in which abatement is allocated across ETS versus non-ETS sectors. So for all of these targets, we have the same EU-wide target, this 55% target. But this 33 ETS target just means that a lot of the abatement is carried out in non-ETS sectors instead. So what I'm not showing you here is the average non-ETS target, but it would increase if the ETS target drops. So this explains why. For your second question regarding the fact that we use a static model, yes, I mean, it's a shortcoming of our paper, that's for sure. I'm not sure how our results would change necessarily in a dynamic framework. What we are thinking about is at least forward calibrating it to 2030. Right now, all our calibration is in terms of 2011, but we're intending to at least forward calibrate. But yes, it's a limitation of our model that it's static. And again, it's the same comment. I think with the labor mobility in the EU, you have labor and capital mobility across borders, right? But it's a simplifying assumption in our framework, and we feel like it's beyond the scope of our paper to take into account a high degree of factor mobility. But it's true that our results might change if we do change that assumption. Yeah.
Thank you. We've got one final question for you.
Yep.
From Mr. Venmans. Do I understand correctly that richer people suffer more from climate abatement? What is the mechanism? This seems contrary to other studies finding that consumption from the poor tend to have more energy, food, and fuel. This question relates to within-country inequality.
Yes, thank you for your question. So this picture takes into account both the use side and the source side. So on the use side, poorer deciles have more emissions-intensive consumption, so they're more hurt by rising carbon prices. But on the source side, it's the richer deciles that are hurt more because they lose more income. And the reason for this is that they derive a larger share of their income from capital and labor that see their returns go down when you introduce a carbon price, whereas poor deciles derive a larger share from transfers that are not as much affected by the carbon price. So you have this trade-off between the use and the source side, and in this picture it suggests that the source side is dominating the use side.
Well, we thank you very much for this interesting presentation.
Thank you very much, and thank you for all the questions and comments. I appreciate it.
Okay, we're going to move on now, and the next presentation is should methane emission regulations be prescriptive or performance-based? And the presenter is Robert Kleinberg from Columbia University and Boston University. Sir, you have the floor.
Well, thank you very much. It's a pleasure to be here at the session of IAEE. Let me share the screen here. And I should be audible now. I hope that's a yes. The topic I'm going to present today is should methane emissions regulations be prescriptive or performance-based? And my request is similar to that of the previous speaker. I'm going to be presenting a enlarged version of this to the U.S. Environmental Protection Agency in the form of a public comment. And so any criticisms or suggestions would be most gratefully received. Here's an outline of what I'm going to be talking about for the next 20 minutes. I'm just going to introduce the topic by reminding you all of the importance of natural gas in the US and global energy economies, and the fact that methane is the main constituent of natural gas. And methane is a very powerful greenhouse gas agent. We're going to talk about that a bit. And more to the point, reducing methane emissions is the quickest way to mitigate climate change. So it's a very, very important part of our atmospheric chemistry. The central part of the talk is that US methane controls have been ineffective. And I think more ineffective than people think. That's going to lead us to a discussion of prescriptive versus performance-based regulation and how these two styles differ from each other. And finally, I'm going to end with a comment on the outlook for Europe and perhaps the Far East with respect to this issue. So this is a chart from the Lawrence Livermore National Laboratory showing basically the sources and uses of primary energy in the United States in 2020. The left-hand column is the sources of primary energy, and the light blue box is natural gas. It's one of the most important boxes on the left side. And not only is it a large box, but it also is one of the most versatile in the sense that about a third of natural gas production goes to electricity generation, about another third to industrial uses, and the balance goes to residential and commercial uses, mostly space heating. So it's used across the economy, and that's true in the United States and of course also in many other countries. Now, as I said, the primary constituent of natural gas is methane, CH4 chemically. And methane is generally regarded as the second most powerful greenhouse gas. After carbon dioxide. But I'm going to contend that it's kind of tied for first with carbon dioxide for this reason. This is a chart, the data of which came from a paper written about 10 years ago by Drew Shindell at Duke University, pointing out the effects of mitigating greenhouse gas emissions. Now, in the reference case, which is the red line that follows the International Energy Agency stated policy scenario that was current at the time he wrote the paper in 2012. And in that scenario, which basically mirrored the Paris Climate Accord, global average temperature keeps increasing, and global average temperature on the vertical axis in degrees centigrade with a baseline of temperature in the 1890 to 1920 timeframe, and the horizontal axis being years, about 60 years in duration. You can see that the base case temperature keeps marching upwards in a somewhat scary fashion. Now, if you have a carbon dioxide abatement scheme, your temperature trajectory will follow the blue line. And again, this is assuming that these abatement measures commence in 2012, the date of the publication of the paper. And you can see that even with a fairly substantial CO2 reduction as prescribed by the International Energy Agency 450 scenario, nothing happens for 30 years. And the reason for that is that carbon dioxide has a very long lifetime in the atmosphere. Once it's there, it stays there. And so even if you cut the current emission of carbon dioxide, there's still a lot in the atmosphere that's continuing to warm the Earth. And you don't really see an effect until 30 years later, as shown by the blue line sort of starting to level out. This is important. On the other hand, if you have a similar abatement policy for methane, a 40% reduction from the reference case, you have the green line. And here you have a temperature reduction immediately. And the reason is that the lifetime of methane in the atmosphere is only about 12 years. So as soon as you cut off the supply of methane or decrease the supply of methane going into the atmosphere, you start getting pretty rapid diminution of methane concentration and therefore its warming effect starts disappearing. Now that's only good up to a point. As shown, the green line then assumes its original trajectory, pointing out that really we need a combination of both carbon dioxide and methane abatement measures. But if we are interested in what our climate is doing from now until 2050, and that has been a focus of recent concern, methane is really the way to attack it. Now, the United States has had methane and in general natural gas emission controls since 2012. And so what I investigated was, have these controls been effective? I would say the results were disappointing. Starting at the chart on the left, the horizontal axis is in years from 1990 to the present. Our latest data is from 2019 rather. The left scale vertical axis is methane emission intensity. And methane emission intensity is the amount of methane being emitted by the oil and gas industry in the United States, divided by the production of gas in the United States. So that's considered a fair measure of intensity. And that's the black line. And you can see that the intensity was pretty constant at about 2% from 1990 to about 2005, and then fell rather rapidly to about 1% at the present time. And that decrease from 2005 to the present very much mirrors, in fact, it is a mirror image of the US gas production, which is in the denominator of the ratio that is the intensity. So in other words, although we have a large decrease in intensity, it is totally driven by the increase in gas production, and that's due to hydraulic fracturing, fracking, if you will. If you look at the chart on the right, it's the same data, but now plotted on a very much enhanced vertical scale. Again, the time scale is the same, 1990 to the present. Vertical scale is now methane emissions itself, not intensity, normalized to the emissions in 2019, which is when these regulations first took effect. And you can see, and the data looks pretty noisy because the vertical scale is exaggerated. But you can see that the data is consistent with a compound average growth rate of about minus 0.3%. This is somewhat disappointing because in 2016, President Obama promised or had a set a goal that methane emissions would fall by 40 to 45% by 2025. That's a compound annual growth rate of minus 6%. So you can see that we are not going to reach a 40 to 45% reduction by 2025 with a growth rate of minus 6% if we're decreasing at minus 0.3%. And more to the point, there was no change in these trends when these regulations started to take effect in 2013. Basically, we're not doing any better now than we were before these regulations, which are very extensive, were promulgated. So this led me to wonder whether we can't do a better job with our regulatory regime. To move on to something that might work better, I've compared prescriptive regulation, which more or less describes what we have now, with a performance-based regulation, which is something much more the sort of thing that economists like, because it's sort of like a cap and trade system in a sense. And in a prescriptive regulatory regime, there's a focus on individual parts and components. You have to use a certain kind of component that doesn't leak very much and replace them and so on and so forth. There are separate rules for leaks, vents, and flares. These are three very different kinds of emission pathways. They get their separate rules when everything is prescribed. Regulators in your national capital write those rules. And regulators are smart people, they're diligent. well-meaning, but they are not necessarily experts in oil field technology. Now, sort of the good thing about prescriptive regulation is that measurements are not required. And the reason we have prescriptive regulations is that until a few years ago, our measurements of methane emissions were not very good, certainly not very extensive. And the Environmental Protection Agency had no approved methods of measuring methane emissions. So hence, if you can't measure, then you're sort of left with a prescriptive format. A bad thing about prescriptive regulation is that compliance is basically unverified. The regulated entity, the company or owner or operator of the infrastructure, is handed a checklist. He goes through the checklist, certifies that he has done all the things on the list, and then hands the list back to the regulator. But no one really knows how effective those changes have been, and you'll see a result of that in a minute. Therefore, suppliers are rated on sort of a pass-fail system, where either you have checked all the boxes or you haven't. That's kind of the two choices. Performance-based regulation is very different. It's a focus on companies, not on components. There's a unified target for all emissions. You don't really care where you're reducing emissions as long as the emissions get reduced. And that gives facility engineers the freedom to figure out how to hit the targets. And they are really in the best place to do that because they are working in the field every day and know their equipment. Now, in order to make this work though, accurate measurements are essential because you need to be able to verify that the engineers are doing the right thing. And that compliance should be verified by validated third-party measurements. When you have this system, suppliers can be rated quantitatively. And this gives importers or buyers the opportunity to discriminate in favor of low greenhouse gas emitting fossil fuel sources. And that's more and more important these days as this issue has gained in importance and prominence. So let's just look at one example of what can go wrong with prescriptive-based regulation. In 2012, the Environmental Protection Agency banned what are called high bleed pneumatic controllers. Now, this is a kind of valve that on purpose and by design emits methane continuously into the air. It does that for technical reasons. We don't need to go into the technical details necessarily, but these high bleed controllers were banned in 2012. And in fact, the industry had already been swapping them out pretty progressively. And the chart on the right shows the methane emissions coming from high bleed controllers in the red bars, from what are called intermittent controllers, intermittent bleed controllers in the green bars, and then low bleed in the blue bars. The intermittent bleed controllers do not emit methane continuously, but only when the state of the valve is changed. So in other words, if the valve is turned on, you get a puff of methane, turned off, you get a puff of methane. Now, the 2012 and subsequent regulations banned the high bleed. So the engineers substituted them with the most economical alternative, which was the intermittent bleed, which were unregulated. So no one told them they couldn't use it, but in fact, the intermittent bleed controllers emit almost as much methane as the high bleed controllers. So in the end, you don't get much environmental benefit from all this activity. Meantime, the low bleed controllers, which really are better, were ignored. So this is an example of how a prescriptive focus on components can lead to unintended and undesirable outcomes. And we're talking about 2 million tons of methane a year, which is 1/4 of the entire methane emissions from the US oil and gas industry. This is not a small problem. On the other hand, if you look at the performance-based method, you sort of survey a company's operations, well sites, processing plants, and so on, perhaps by aircraft or ground-based mobile platforms. and actually measure what's coming out of them. And this has already been done by the Environmental Defense Fund, private NGO, which has surveyed almost the entire Permian Basin, which is one of the world's largest oil fields in West Texas and New Mexico. And they have made maps showing every facility that is emitting methane at measurable quantities and how much they're emitting. So all you need to do is go to their website, which is permianmap.org, click on the company of your choice, and you will see how much methane they're emitting. So if you ask the companies adhere to at least the average, then pretty soon everybody is going to be performing at least average level. And that would be a big improvement over what we have now. Now you might ask, are these measurements accurate enough? And the answer is yes. This is an example on the right of a calibration run that was run by Kairos Aerospace, which is a commercial entity that sells airborne-based methane emissions measurements. And on the horizontal axis is the amount of methane emitted in a blind test from a ground facility that the airplane flies over and then reports what it determines the emission rate to be. And you can see that there is a bias. The dots fall on a line that is not on the 45-degree line, but above it. But this is a kind of bias that's pretty easy to calibrate out. And you can see the precision is actually pretty good. These measurements are getting better every year. And as they get better, we'll be able to hold the operators to a higher and higher standard. Now, what about Europe? Well, the European Union is very interested in the greenhouse gas footprint of the fossil fuels it imports, and it is the world's largest importer of natural gas. And they have estimated that their greenhouse gas footprint, 3 to 8 times more emissions are coming from outside the European Union than from inside the European Union. So they're really importing their problem, essentially. And therefore, Europe must influence the behavior of fossil carbon exporters. Now, they are presently writing regulations, which then have to be applicable to the rest of the world to comply with World Trade Organization strictures. I'm going to challenge, now so far we haven't heard much from the Asian importers, which are also very large importers of fossil fuels. And I'm going to challenge the Asian importers to step up and show leadership in the same way that Europe is.
2 minutes.
Right. So I'm just to end up with some observations and conclusions. I've worked in the oil and gas industry for 40 years, and I can tell you from personal experience that engineers are really good at complying with the letter of regulations at lowest possible cost. So that means that regulators have to ask for exactly what they want. Now, regulators and the public at large are not particularly interested in the kinds of valves that are used in oil field installations, but they are very interested in the amount of methane being emitted. And therefore, the regulations have to address methane emissions and not a checklist of components to modify or replace. Then we give the operators the flexibility to reduce total emissions in the best and most economical way for their local circumstances. Remote sensing technology, which these days is airborne or ground-based or continuous in-place sensors, is improving rapidly. And that gives us the opportunity to escalate requirements for methane reduction as these remote sensing techniques improve. Finally, fossil fuel users will look for verifiably reduced environmental impact, while fossil fuel suppliers will look for verifiable competitive advantage based on the fact that they are cleaner and emitting less greenhouse gas than a competitor. So to make this work, measurements need to be uniform across basins, nations, and even internationally. and made by third-party service organizations certified by national or international authorities. So at the bottom of the screen, you'll see reference to a very much longer paper I recently posted on the Social Science Research Network, number 3860311. Please look at that for more details. I welcome questions during this period. And also feel free to contact me at my email address shown in red on the final slide. So thanks very much for your attention and looking forward to the conversation.
Thank you very much. My immediate question, or maybe just comment, and you've said you had a lot of experience with regulation, as I have. The regulators write rules. That's true, but I hope that they listen to people before they write the rules. So were you expecting, or were you suggesting that there were exogenous things like political concerns that entered into regulators writing rules versus engineers and more technical people coming up with a good reason for writing the rules?
Sometimes you do see that. And I can point to a few very specific, overly prescribed rules that clearly seem to have benefited a vendor here and there. I'd say by and large, the civil service people, the professional career staff people at Environmental Protection Agency are pretty much on the level. The ones I've dealt with seem to be very serious about doing the best possible job. But you know, they inevitably, I mean, there's a million wells in the United States and then many millions more worldwide. And it's impossible for any group of people to understand all the problems and the variety of problems and possible solutions that can be drawn upon to solve a problem like this. And therefore, that's why we need to mobilize the ingenuity of thousands of petroleum engineers that are out there who like solving problems. You just need to give them the right incentive, and that's something economists know a lot about.
Very good. I certainly agree with that. Any other questions or comments? Well, hearing none, I think we'll move on, but we move on with thanks for a very interesting and thought-provoking paper.
My pleasure.
Okay. Our next presentation is reconciling the Pigovian and Sandmo principles of emission pricing. And the presenter is Rausch McKitrick of the University of Guelph. Sir, you have the floor.
Okay, thank you. Now I just need to find my presentation here. There we go. And start the slideshow in the usual way, and hopefully you see the screen you're supposed to see.
I see the screen and perfect.
Okay, we are in business.
Moving along.
So this is more of a theoretical paper than ones that we've seen up till now. And as much as possible, I'm going to just bury all the math in the paper itself and just proceed graphically to emphasize the intuition. So most economists know just enough about the Pigovian principle to get pollution pricing sort of right, but still wrong in an important way, or several important ways. And as a result, there are important policy applications that get mishandled, and that includes cost-benefit analysis and the newer topic, carbon border tax adjustments, and also issues related to combining instruments, charges, and regulations. So the path to understanding pollution pricing begins with Pigou, but it goes through a paper by Sandmo in 1975. And so that's what I want to begin by explaining. This is the textbook model of pollution pricing. So we have a horizontal line there representing the marginal damages of emissions. You could think of that as a social cost of carbon in the climate application. And then there's a downward sloping line called marginal abatement costs. And that's, it looks like a demand curve. If you go out along the horizontal axis, which measures emissions, to E bar, that's the unregulated emissions level. And then as you reduce emissions, the marginal cost of emission reductions are going up. So we read this from right to left, and you have an increasing marginal abatement cost schedule. And in the standard analysis where marginal damages equals marginal abatement cost, you have both an optimal price, the tau star quantity, and an optimal emissions quantity, E star. And so leaving aside the issue of cost effectiveness and equalizing marginal abatement costs across sources, this gives us our notion of the optimum. So you want to equalize marginal damages and marginal abatement costs. So among the implications, if you have a situation where you have unregulated emissions with positive marginal damages, it's always welfare improving to reduce emissions. Another implication is if an abatement policy costs less than marginal damages at the margin, it should always be implemented. And that would guide cost benefit analysis. And a third implication would be if marginal damages are the same across multiple jurisdictions, then every one of those jurisdictions should have the same emissions price. And that would then feed into calculation of border tax adjustments. Now, in a paper in 1975, which didn't get a lot of attention at the time, but a very important paper, Sandmo revisited this analysis, but looked at the case of what happens if you have taxes in place already. So what if you have an existing tax system and then you have externalities? And among the results that comes out of that model is that the optimal emissions price should be the marginal damages scaled by the marginal cost of public funds. Now, the marginal cost of public funds, there are more precise ways of defining this within a general equilibrium model, but you can think of it as the loss of private sector welfare in order to increase the public budget by $1. And you can think of it as 1 plus the marginal excess burden. Variety of ways of defining it, but generally speaking, when you're using typical tax instruments, the marginal cost of public funds will be greater than 1. So the private sector loses more in welfare than the money value increase in the public budget. And estimates can easily be 1.5 or higher for economies' tax systems. And so that implies the optimal tax is below the Pigovian level. So what's missing in the simple textbook Pigou analysis? Marginal damages refers to the social cost of the pollution emissions. Marginal abatement cost refers to the private cost of abatement. And the marginal abatement cost only equals the social abatement cost if the marginal cost of public funds equals 1. Otherwise, the social marginal abatement cost curve would sit above the marginal abatement cost curve. So in our Pigou diagram, adding in the second order effects, or the second best effects, means the social marginal abatement cost curve looks like that. So the optimal emissions is out there where the social marginal abatement costs equals the social marginal damages. And that means tau star is no longer the optimal price. Instead, we need to scale it down by a factor. So I'll call that the coefficient A. We multiply marginal damages by the coefficient A. And A in the Sandmo outcome is the inverse of the marginal cost of public funds. And that result has been re-derived by many subsequent authors. It assumes that we are using taxes and not tradable quotas. This is not a cap and trade model. And that's important because if we're using taxes, the revenue goes to the public sector, and then the government can still optimize the tax system by applying reductions in other tax rates. And it also assumes we have no other emission reduction policies in place. So this is an abstract situation, right, where we don't use quantity regulations, we're using just emission pricing. So what happens if those assumptions don't hold? Well, we get what's called a damage threshold case or a corner solution. And back in the 90s, there was a series of papers. Environmental economists got really interested in these second and third best cases. And then the literature kind of died out in the last decade without really coming to a resolution. But I'll give you an illustration with the social cost of carbon of what happens if those other assumptions don't hold. The change from the private marginal abatement cost curve to the social marginal abatement cost curve isn't just a rotation, it's a translation. So the whole curve shifts out to the right, but then we add in a proviso that you cannot subsidize emissions. You would never want to go above the unregulated emissions level. So that means we truncate the social marginal abatement cost curve, and that yields this damage threshold. And so among other things, now our optimum is in the red circle area. So that means there's a further adjustment to the optimal emissions price. But it also means that there's that damage threshold, and marginal damages have to exceed the threshold for the first unit of emission reductions to be welfare improving. So here's an example from a paper in '96 by Bovenberg and Golder, computable GE analysis of the US economy. And these are marginal abatement cost curves, but they're mirror image because along the horizontal axis, it's not showing emissions, it's showing emission reductions. So I can make this look like the existing format. So now we have what look like marginal abatement cost curves. That bottom graph shows the optimal version of it, the Pigovian analysis, where or the Sandmo analysis, where we have an optimal tax system and you recycle all the emission tax revenue. Then if you recycle the tax revenue, but you don't optimize the labor income tax, then that line shifts up a bit. And then the third line up is what if we use something like cap and trade instead, or lump sum rebates of the tax revenue? Then as you extrapolate those lines forward, you would get to those positive threshold measures. And in the case of the top line here, if we're using non-revenue raising pricing instruments, you get the intercept there is at about $55 a ton. So their argument was, unless marginal damages in this case exceed $55 a ton, the first unit of emission reduction would be welfare reducing. So the actual formula then in the second and third best case for the optimal tax rate is that the optimal tax should equal A times marginal damages minus B, which is a new parameter. And B can be negative. It can be negative or positive. And then the social optimum occurs where marginal damages equals the social marginal abatement cost, which is a transformation of the private marginal abatement cost. And then the threshold then is the ratio of B over A. So in the paper, I go through a new derivation of all these points just to try to explain where they come from. What are the implications? So the first is that the standard Pigovian rule never applies, at least not in any known real world economy. So it only applies if the coefficients A equal 1 and B equals 0. And these you can rule out for any realistic economy that we deal with. The second is, this is the point, it appeared first in that Bovenberg and Golder paper. Interestingly, it appeared in their numerical simulations, but not in their theoretical models. So they had to discuss where it was coming from, but they didn't try to generate it theoretically. That came in a subsequent paper. What it means, if the social cost of carbon is less than what would be about $75 in today's money, then any non-revenue raising climate policy is welfare reducing. You can get around that if you shift to fully revenue raising climate policies, and especially if you do revenue recycling through the tax system rather than funding other spending. And then the third point is that social cost of carbon is the wrong measure to use in cost benefit analysis, and using it would lead to excessive regulation. Okay, I want to talk though about another implication which I haven't seen discussed anywhere in the literature, which has to do with carbon border tax adjustments. So even if the social cost of carbon is the same everywhere, the marginal cost of public funds is not the same everywhere. So every country in principle should have a different optimal carbon tax. And that means that the basis for computing carbon border tax adjustments needs to take account of the different marginal excess burdens. It's not enough just to look at two jurisdictions and conclude that one either has a higher carbon price or more restrictive policies than another. Therefore, it has a case for imposing border tax adjustments on another jurisdiction. So here's a paradox. Suppose we have two countries and country X has a low carbon price or equivalently a weak emissions policy compared to country Y. It's not necessarily the case that country Y would be justified in charging a border adjustment on country X. In fact, it wouldn't be hard to construct a case where X would have a case for imposing a border tax adjustment on Y, even though it has the lower carbon price. And the reason has to do with what are the characteristics of the tax system in the two countries. So two further implications here. First is that when we're using non-revenue raising pollution regulations, that damage threshold Z is always greater than 0. So if we, again, in the simple Pigovian analysis, people will tend to think that it doesn't matter what instrument you use, as long as you get to the optimum. It doesn't matter if you use cap and trade or emission taxes or even well-constructed regulations, they're all symmetric. And that's no longer true in second best analysis. If we use non-revenue raising pollution regulations, the damage threshold is always above 0. However, you can cure that welfare loss if you follow it up with an emissions tax that essentially overtakes the regulation and replaces it. And also at unregulated emissions level, the standard economic analysis would tell us that emission taxes are marginally less costly than regulations. But if we're heading for 0, if we're going for extremely aggressive emission reduction targets, there is a point where that ranking has to reverse. And after that, regulations would be marginally less costly than emission taxes, which is a paradox for anyone who's familiar with the standard comparison of instruments. But that point was brought out in a later paper by Larry Golder. Very interesting result, I think. Okay, so my conclusions here, and I have saved you from the ordeal of all the math, but you're welcome to see it in the paper that I posted at the conference website. Most economists and many non-economists understand the basic Pigovian principle, but the fuller picture that came out through all the second best analysis and the general equilibrium theory really changes it. And proper application of emission pricing requires analysis of the economic context within each jurisdiction. And I will stop there, and that leaves us with some time for questions.
Thank you very much. Okay, and let's see, we've got several items in the chat that down at the bottom here. I would think that it is the inverse if we take into account that $1 of efficiency improving carbon tax reduces the need for inefficient other taxes which have a dead weight loss.
Yes. In the original Sandmo article, he talks about this because it's counterintuitive. Why would it be the case that in an economy with a higher marginal cost of public funds, you would then have a lower emission tax rate? The way to think about it is that the setup theoretically is that emissions abatement is like a public good. So in fact, it's mathematically identical to the Samuelson public good model. It's just the labels are changed and there's a minus sign. So you can think of it as funding public goods. And in that context, in a country with a higher marginal cost of public funds and a costlier tax system, you would not fund public goods as much because it's the welfare costs are higher of doing so. So that's how you get this result that the higher the marginal cost of public funds, the higher the social abatement costs are, because it's functioning like a public good.
Can I reframe my question again? So like it relates a bit to the double dividend.
Mm-hmm.
So I would start from a reasoning where there is no deadweight loss for any tax. But now I take into account that there is the standard taxes have this deadweight loss, right, and my carbon revenue is going to replace these standard taxes. I have my double dividend.
Yes.
And I would think that I want to have that it's like an extra argument for carbon tax. I would like to tax even more, or at least be closer to the efficient level of carbon taxing.
Yes. Okay. Now I understand. Yes. So you're right. And there was a literature in the late 1990s that made that exact point, and people had to go back to the Sandmo article at that point and try to figure out, okay, what you said makes perfect sense. What's missing in that argument is what are called the tax interaction effects. So you put in place the emissions tax. It now raises the costs of other goods and reduces real wages. And in doing that, it's going to have an effect that exacerbates the deadweight loss in those other markets. Okay. So it's those second order tax interaction effects that if you didn't have those, so if you didn't have deadweight losses in the other markets, you would be right. You would then want to overprice emissions, although you wouldn't be recycling the revenue through factor income taxes there. But with factor income taxes, because those markets are so large, it doesn't take much of an extra distortion in those to generate this large offsetting tax interaction effect.
Okay, thank you.
Yes, thank you. Okay, well, we want to get back to our speaker. Okay. I'm not sure why we reduced Rausch to a postage stamp, but we thank you very much for your presentation.
Okay, my pleasure.
You're back. Well, again, thank you very much. Okay, we need to move on. And so we'll move on to our last speaker. And okay. Our final presentation is reducing carbon emissions of households through monetary incentives and behavioral interventions. And our presenter is Tarun Khanna of the Hertie School. Sir, you have the floor.
Hi, thank you, Robert, and it's indeed it's really a pleasure to be here and present this work. What I'll be presenting is a joint work done with colleagues at the Mercator Research Institute for Global Commons and Climate Change in Berlin. It's a joint work paper that would be published in the upcoming, hopefully in the upcoming issue of Nature Energy. So just to set the context a bit, several people have pointed, in the literature have pointed out to the overwhelming focus on supply side in decarbonization pathways, so technologies, decarbonization of the energy supply, etc. And there has been pointed out that we potentially also need to focus on the demand side to reduce the sort of overwhelming dependence on supply side technological solutions. An important work in this regard also comes from Dietz and Paul Stern from 2009, where they sort of set out this broad literature and gave sort of broad estimates of what can we potentially expect insights from psychology and behavioral studies to talk about energy conservation and the role that it can play in the carbon emissions mitigation in the United States. Of course, this literature is, as probably is well known to several of you, is quite a vibrant literature. There are perhaps thousands of different studies focusing on different parts of the economy, and with various estimates on what kind of emission or energy conservation, emission mitigation are possible using insights from psychology and behavior economics. So for us, I think the starting point was, so how can we really synthesize this literature a little better and in a systematic manner to understand what does all this evidence on behavioral interventions and behavioral change imply for the climate assessments. In this particular analysis that I will talk about today, we focus essentially on behavioral change of households in residential buildings. Why residential buildings? Well, they are a fairly important source of carbon emissions and account for up to 28% of total direct plus indirect carbon emissions per year. Residential buildings are overwhelmingly the most important source within the building sector and contribute to up to 5.5 to 6 gigatons of CO2 emissions every year. Again, there have been several, this is in fact a vibrant field of debate as to whether we actually need demand side measures or not, given that there are some stagnation in demand across several economies. But at an aggregate level, what this graph shows actually is that there was indeed some sort of stagnation in the early 2000s, but building emissions are again once on the rise, and the trend probably would continue with greater electrification in the developing world as well. That's perhaps to be expected. Okay, so with this paper, we try to look at only a smaller segment of the policy interventions targeted at household behavior. So we look at any sort of intervention that targeted household energy consumption in houses, but tried to modify their behavior around daily use activities. We looked at both monetary and non-monetary interventions. So the monetary interventions would be the sort of typical energy economics interventions of time of use pricing or some sort of pricing mechanism to incentivize consumption at the right time of the day or at the right moment of the year. Of course, a lot of the emphasis in such experiments is not so much on energy conservation as a whole, but rather on demand shifting. But as we will see in this in our analysis, it has been reported also in several of the primary studies such sort of time of use pricing usually not only leads to demand shifting, but actually overall demand reduction by the households. So it's in some sense important, almost like a side effect of these time of use pricing experiments, but which is one that is highly relevant to the climate debate. Besides monetary interventions, we also look at a wide range of non-monetary interventions stemming from the literature in behavioral economics and psychology. We classify these into 4 different categories. So one that explores the sort of informational deficit of households. So, households just don't know how much they should or how they can reduce their energy consumption. So by giving them information, tips, reminders, doing home audits, we can actually give them the means to reduce energy consumption. Another branch of these experiments talk about the sort of lack of attention of households on these issues. So if you provide households with targeted information which focuses their attention on how much are they actually consuming, say by telling them how much they consumed over the last 1 year, it actually can reduce their energy consumption. The third set of trials and experiments looks at the role of peer effects in energy consumption. So to what extent can providing home comparison of a household's consumption with its peers through home energy reports in forms of some sort of normative feedback really induce households to reduce their energy consumption. Again, this is a literature which has several experiments being done both in psychology and behavioral economics. A modification or like sort of additional literature on these comes from also increasingly and interestingly from the engineering literature, where a lot of home display systems are being experimented and tried out. Smart metering solutions which also display the energy consumption and compare it in real time with and with different parameters. So there's a vast literature that has sort of come around in the engineering sort of and management sciences around these interventions as well. And lastly, which is again sort of like a growing field within this literature, is of experiments that use some sort of motivation or goal-setting devices to incentivize households to consume less energy. An example of this would be mobile apps or games that can help households reduce energy consumption. So what we're looking at when we look at all this literature, basically we wanted to synthesize literature to answer three basic questions. First of all, by how much can monetary incentives and non-monetary interventions reduce consumption of households in residential buildings? So what is the average treatment effect out there? Which interventions are most effective and under what conditions? What can the evidence tell us? And by how much can CO2 emissions be reduced using such interventions, as I already mentioned before. We do so using a comprehensive machine learning assisted review of the scientific literature. Let me sort of give you a brief snapshot of how we went about this. We did a systematic bibliometric search and search also on bibliometric databases, Web of Science, Scopus, Medline, JSTOR, and came broadly with a set of about over 60,000 research articles and trade literature that was potentially relevant, and it contained quasi-experimental or experimental evidence or quantitative estimates of the impact of these interventions. Clearly, this was a very large data set to deal manually with. So we applied machine learning techniques to prioritize the screening of this literature and eventually manually screen about 1,000 studies to extract the quantitative estimates from these studies of the impact of behavioral and interventions in energy consumption. So what do we sort of find? Well, we find that these sort of, on an average, when we look at the literature as a whole, we find that interventions have a small to medium effect on household energy consumption. The graphs on this slides give you a little bit more detail. So on the left-hand side is a table with the average, with our estimates from the various meta-regression models that we ran. The dependent variable in all these analyses is Fisher's Z. That's sort of the metric that we use to standardize the results from all the various different studies and indicates the strength of correlation between energy reductions and the interventions. So a Z greater than 0 indicates reduction in energy demand here. We find that on an average in the literature, the average effect size varies between 0.10 and 0.15. Now, just to sort of contextualize this, the relevant literature, or in fact, all the literature in psychology and social psychology has an average treatment effect of somewhere around 0.20. So while this this number is not very large, it is relevant. It can be considered as a relevant. 0.10 can be considered as a small effect that is relevant when scaled up, and 0.20 can be considered sort of like a medium effect that is relevant even in the short run and over sort of medium-sized populations. So we believe that the overall effect that we are looking at with this literature is a small to medium effect of these interventions. The graph on the right-hand side is potentially also interesting, where we try and isolate this average effect size by subsets of the interventions that we looked at. So what we see is that the average effect size of monetary incentives, that only had monetary incentives, is around 0.20, so sort of a strictly medium-sized effect, which is relevant even for relatively medium-sized populations, versus a relatively small effect for social comparison and motivation-based experiments, but however, which can get relevant when scaled up and applied on larger populations. Both with feedback and information, we find a relatively medium-sized impact on an average across all the studies. Interestingly, our data set also allowed us to look at not just individual interventions, but also how they are combined. So within this literature, it's almost very, very common to see more than one intervention being deployed at the same time in an experimental setup. And using the data that we collected, we were able to compare these in a meta-regression model. What we find is that there are definitely combinations and packages where the overall effect, which are complementary in nature, and the overall effect is actually higher than individual interventions. So, for example, studies that combine feedback, social comparison, and monetary incentives give an average effect of about 0.35, which is higher than the average effect from when these interventions are applied individually, though it's slightly lower than the linear sum of the individual effects of these three interventions. So there's definitely some, so these interventions are probably complementary, but not strictly linearly additive, at least the effect size that we see in the literature.
5 minutes.
Thank you. We do also find evidence that not all interventions, however, can be combined very successfully. And in several of the combinations, there seems to be no reasonable amount of gain in applying the combination versus the individual packages. However, why these effects vary is something that has been talked about in the literature, but has not been systematically studied in quantitative studies, and that is something we believe should be next. So in the last part of our paper, we try and synthesize these various estimates to give the average emissions reduction potential of these interventions, and we estimate that to be around 0.35 gigatons of CO2 per year, which is fairly modest compared to the overall emissions of residential buildings. Of course, nevertheless, it has some role to play in short-term emission reductions. We do believe, given the lack of literature or lack of literature on long-term trials, we have only sort of looked at the overall effect for between 3 to 5 years. I think longer term estimates are still needed. We, however, do think that this is a conservative estimate because in different contexts, so for example, by combining interventions or by limiting demand growth in developing countries, such interventions may actually have a slightly higher effect. Further, we don't look at structural change in buildings, and that could be even higher. This is actually the work that we plan to do next. So we sort of want to look at a broader spectrum of all the interventions and behavioral change across energy, transport, and food in the residential setting. This is the work that we plan to do next, and we are collaborating with other institutes in taking this work forward. I would just end by saying that we have some interesting findings for what can be improved in these studies. So for example, it seems it's very important to look at study design. So using relatively sophisticated statistical methods is important because there seem to be systematic differences in the results from these studies versus more simple designs. And different designs, for example, also are super important. We don't find as much evidence for the importance of study level controls outside of weather in studies that look at monetary incentives. I think perhaps I will end here, and we can have a lot longer discussion in comments. Feel free to also reach out to me post the presentation. Thank you.
Thank you. I was particularly noting a comment you made at a couple of slides back that maybe the best incentive could be in the ability to, or the encouragement to change structures. Because I'm thinking that there's only so much that we do within our homes and our businesses, but if we have a different structure in which to operate, we may have a greater overall change. So I thought that was an important point. Are there comments or questions from our colleagues? No. Well, it's been the end of a long day for some of you who are in Europe or elsewhere. Those of us in the United States are about to have lunch. So perhaps this is an important and auspicious point to thank all of our speakers for their contributions to what has been an interesting day and an interesting session. And I wish all of you good luck with your work, and wish you a good rest of the conference. Thank you very much for your attention and participation.
Thank you.
Thank you for the session.